Now we are ready for Gauss Theorem. We are waiting for this from a very long time. So now this time we are ready. We have already got all the tools to define this. So now the statement of Gauss Theorem is in front of you. As we know that the surface integral of an electric field intensity over the closed hypothetical surface, which will call later the Gaussian surface, in free space is equal to the 1 upon epsilon naught times the charge enclosed by that surface. Or in a mathematical form we can say that phi is equal to the closed integration E dot ds is equal to 1 upon epsilon naught times the summation of the entire charge enclosed by that hypothetical surface. Let Qi be the charge enclosed by the hypothetical surface. Now we are ready to do the derivation of this part, that is the proof of Gauss theorem for a spherically symmetric surface. So let us consider a spherical body surface, and now the plus q charge is placed at point O, and there is an elementary area at a distance small r. Now we can say that there is ds vector represents that area, and it is radially outward with respect to the point O. Now the field at that point will be also along the direction of r cap. So we have already discussed about the flux passing through this area will be given as d phi is equal to E dot ds is equal to, as we know that the electric field at a distance r with respect to the original point is E is equal to 1 upon 4 pi epsilon naught q upon r square. So our equation becomes 1 upon 4 pi epsilon naught q upon r square r vector dot ds n cap. As we know that the normal vector and radial vectors, this one, it will be written like this: d phi is equal to 1 upon 4 pi epsilon naught q ds upon r square r cap dot n cap. Here r cap dot n cap is equal to 1 because the magnitude of r cap is 1 and n cap is 1, and the angle between these two is 0. So the cos 0 will gives you 1. So overall r cap dot n cap will be equal to the 1. So therefore we can write d phi is equal to 1 upon 4 pi epsilon naught q ds upon r square. Now we are looking for the total flux. So what we have to do, we have to integrate it. So that will be phi e, that is total flux, will be equal to the d phi, the closed interval for the surface S. We can say that it will be like this: 1 upon 4 pi epsilon naught q upon r square. That is the term which will be the constant for the entire point which are situated on this Gaussian surface. Since all the points are at a same distance with respect to the charge, so that is to be taken out, and there is a closed interval ds. So as in the Gauss theorem we have already stated that the value of this ds for the closed surface is numerically equal to the 4 pi. So now we will put here. So what we will get, 1 upon 4 pi epsilon naught q upon r square 4 pi. Is it clear? So the 4 pi is cancelled out through the 4 pi, and the r square is to be through the r square. So what we will get, that is equal to the q upon epsilon naught. It means the total flux phi e is equal to 1 upon epsilon naught times the q. In this figure only the q charge is here, so that's why we have written q. If we put the more than one charges inside the region, then we can say that the total flux will be 1 upon epsilon naught times the summation of q. In the upcoming video, we will talk about the application of Gauss theorem one by one. Till then, bye bye. Take care.